Alrighty, what are we doing? So we're sketching the graph of the derivative of a function. We got into this a little bit the other day at the bottom of our notes, but these are going to be a little bit more interesting. So we're given a function, asked to sketch the graph of the derivative. So we really need to evaluate what is the slope at different points in time, and then sketch that on another graph. I scaled the x-axis, and you should scale your x-axis similarly, so I'm going to make this -5, this is 3, this is +5, and +7. Okay? So if you're looking at the original function, is there any point in time where you can tell me exactly what the slope is? The exact value of the slope? Aaron?
X equals 0 and x equals 5.
Right. At 0, what's the slope?
0.
0. So at 0, our slope is 0. So that's going to give us a point on our derivative curve. So we've got this. And also he said at 5, the slope is 0. So at 5, we have a 0 slope. Okay? Let's talk about what is the slope in between those. It's constantly changing, right? It's not the same slope the whole time, but it's always what in between here and here? Negative. So when we go to our function over here, our derivative graph, we should be negative in between here, right? Initially, it's barely negative. And then at what point would you say it's the most negative? Tell me when to stop. When is this the steepest it's going to be negative? You didn't tell me to stop. So here it's barely negative. Can we agree with that? And then somewhere in the middle, right? Okay? So somewhere in the middle, maybe we'll just say it 3 to make it becomes the most negative it's going to be. Maybe it's slightly before 3. Because if you kind of looked at a progression of tangent lines, if you did the tangent line right there, yeah, that's a negative slope, but it's not as negative as it's going to be if you draw your tangent line down here. That's more extremely negative. So between 0 and 5, it's negative the whole time. So we have to be under the x-axis to be negative. Probably becoming most negative just before 3. Okay? And just before 3 would say there. That's when it's going to be the most negative. So it's almost like it's the derivative curve is actually going to reach a minimum there, because it's most negative. Now, I'm not going to scale my y-axis because I have no idea what the actual value of that slope is, but I know that it's about the most negative. Usually you're going to find that the most negative point is halfway between a max and a min. Does that make sense? Okay. And for the record, this is kind of a different topic that we'll get to later in the year. What actually happens at that point, where we become as negative as we're going to get, and then we start to balance out again and back approaching 0 again, approaching a slope of 0, is we talk about concavity there. You know the word concave from science, right? Concave lenses, convex lenses. Concavity is really whether it's opening up or opening down. So up until this point, I would say it's a part of this section of the graph where this is opening downward. And then your concavity switches there, and I would consider it part of the graph where it's opening upward. Okay, so it's I think point of concavity where the concavity changes is going to equate to a minimum, in this case, on your curve, on your derivative curve. So far, so good? Okay. What happens to the slope at 5 and beyond? positive. And slightly positive at first, but it's constantly going to get steeper and steeper and steeper, yes? Does that make sense? So, and that's just naturally going to happen. When we first, this curve is going to be a continuous, nice, smooth curve. As we pass 5 immediately, of course, you're at a small number, so your slope is pretty slightly positive. But then as you continue, your slope continues to increase indefinitely as this gets more and more like a, more and more looking like a straight vertical curve. Okay? And also prior here. What is our slope? Lauren, what can you tell me about your slope in this stretch? Prior to 0. It's also positive. We're going up, 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 up. Extremely at first, and we're still positive here, but not as much. And again, that's going to happen where as soon as we get to the left of 0, we have a positive slope. Not that positive. It's pretty slightly positive, but as we continue going towards negative infinity, our slope keeps getting higher and higher. So these y values keep getting higher and higher because our slope keeps getting steeper and steeper. Follow? All right, so we're done. That's it. That's all we're going to do, because it's a positive slope forever in the negative direction. So we're in the positives forever in the negative direction, and also it's a positive slope forever towards infinity. Just a quick note, because I keep talking about it, although we won't officially see it until Monday, but what is the degree of this function? If that's just a basic polynomial function. Is that a quadratic? Is that of a degree of 2? Yes or no?
2.
No. Nope. A degree of 2 would be a plain old quadratic, and that's got more going on than a quadratic. How many roots do you have? 3, so that's a decent indication. It's a cubic, okay, has a degree of 3. It's obviously odd because the end behavior is opposite of each other, starts low, ends high. And we have kind of 2 different fluctuations, which indicates a degree of 3. What is the degree of this function? 2. This one is definitely looking like a parabola. And that is something common that you're going to see. If your function has a degree of 3, the derivative of your function is typically 1 less. Okay? Any questions? We're good. All right. Next graph might be easier. I don't know. Again, I want you to sketch and scale accordingly. Pretty much everything here is happening. Something happens at -1, at -2, at -3. So I'm just going to scale that way and label this my f prime of x function. All right, Bryce, tell me one thing about the slope at any given interval or point on here.
At x equals -2 and 0.
Is it? Someone tell him, unfortunately, why he's not correct about that slope right at that point being 0. Maggie? It's a sharp point. So actually the slope does not exist there, which is going to be interesting. What about, we'll start left to right, Bryce L. What is, in this interval, from here to here, from -3 to -2, what is the slope of this? Negative. Specifically, though, negative what? You can actually tag a number onto this. What's the rise and run if you count from this point to this point? How many are we going down? How many? We're going down 1 unit and over...
2.
Only 1, from -3 to -2. So down 1 over 1 is a slope of -1. So in that stretch from -3 to -2, it is a linear stretch of graph. So our slope in that moment is constantly -1. So here I can scale my y-axis because I have some points. So from -3 to -2, my slope is -1. But I did use open circles at -3 and -2 because the slope at a sharp point is undefined. Then what happens with my slope from -2 to -1? Alec, what's the slope here?
It looks like it's, 1.
Positive 1. Yep, we're just going back up the other way. This is -1, 1. So your slope here in that stretch is positive 1, which is going to bring us up here. Again, with open circles at -2 and -1, because the slope doesn't actually exist at those sharp points. And then, Lauren, what's my slope in here from -1 to 0? -1, so my slope is -1 in that stretch. So I'm going to have a constant slope function at -1. We see what's happening here? It's just every other interval. Now from 0 to 1, it's positive 1 again. So from 0 to 1, I'm going to have an open circle to an open circle at positive 1. And then from 1 to 2, it's -1 again. And from 2 to 3, it's positive 1 again. And a big key here is that we have all open circles because of the function coming to a point and not being differentiable at any of the integer values. It's only differentiable in between. Was that fun? Alec, on a scale of 1 to 10, how fun was that?
Thrilling.
What?
Thrilling.
That's not a scale of 1 to 10.
Thrilling.
Yeah. I thought that was a little bit easier than the first one. It is easier when you have linear segments, because then you're just going to have flat lines. Because if you know it's a linear segment, then the slope is the exact same number along that entire interval, and that gives you a flat line in your derivative. Okay? Last one. Given the derivative, we're going to work backwards. If the last one was thrilling, Alex, this one's going to be off the charts. Just an FYI. Just to get you all pumped up out there. I can see it in Emily's eyes. She is pumped up. Well, hello, Mr. Gallagher.
How are we doing?
You know Mr. Gallagher was a math teacher? No.
Isn't that impressive?
They're not. Yeah, Dylan gave you a little nod, but that's all you got.
No.
Graphs of derivatives today. It's a big day.
Big day.
All right, so we're going to go backwards now. So this is telling us what the slope of our function should be at different moments. So again, I've got a scale for a reason, so I'm going to kind of use the 2, 6, and 10. Okay? And there is definitely going to be more variation working backwards, okay, if this is like an open response. When I look at this derivative function, the derivative is 0 right here. So at 2, I have a slope of 0. Over on my graph, don't write this down until you decide which way you want to go. At 2, I have a slope of 0. So that could be, it's probably going to be a max or a min of some sort, and who knows where it's going to be. but at 2, I have to have a slope of 0. Do we follow? We also have to look at what's happening surrounding 2. So slope of 0 at 2, which means it's a max or a min. What is the slope prior to 2? Is it positive or negative? Are we in the positives or are we in the negatives? Negative. So the derivative is negative prior to 2, meaning the slope of our function needs to be negative prior to 2. So is it a max or a min? In which scenario is the slope prior to 2 negative? When it's a minimum, exactly. So I'm just going to use that top one. I can no longer use these two because I know it has to be a minimum. And again, there's going to be some variation. So where you place everything doesn't really matter. Everyone's could be looking the same shape but shifted up or shifted down. The actual location doesn't really matter. I'll just go with that top one. So prior to 2, and forever, I should say prior to 2, this is a negative slope that just keeps getting, well, the magnitude of your y values here just keeps getting more and more negative, which means your slope of your function, as you move to the left, it just keeps getting steeper and steeper into the negatives. Okay? From 2 to 10, we're still in the negatives. So actually, this isn't going to wrap around, because that just, the way I wrap that around, that just became a positive slope. But this is telling me that I have a negative slope prior to 2, and a negative slope after 2 as well, for this whole section up until 10. You with me? Right at 2, it is a slope of 0, so what actually does happen here is it kind of wiggles right there to have a quick slope of 0, but then it keeps being negative. And it's going to be the most negative at 6, which is going to be kind of like our point of concavity. So we're going to go crazy negative to 6, 6 being the most negative we're ever going to get, and then our concavity is going to change, and we start to even back out as we approach 10. Still negative in the whole process. Our slope is still negative as we lead into 10. But right at 10, we should have a slope of 0, so that should be like a minimum again. Right at 10, slope of 0. And then after 10, our slope has become, our derivative function is now in the positives, right? So our slope should become positive, which indicates that this does turn around. Holy moly, right? It's a little bit harder. Now, anybody's graph should look like that, but could be shifted up or down as much as they wanted. Does not really matter. Okay? But if you look at it backwards, because I think as a checking mechanism, that's the easier direction to go. You see, okay, I have a slope on my original function. This should be f of x. I have a slope of 0 at 10. So go to your derivative curve, and you should have a 0 there. I also have a slope of 0 at 2. And sure enough, I do. In between 2 and 10, it's constantly negative. So make sure in between 2 and 10, it's constantly negative. After 10, the slope is going to be positive forever. So after 10, this graph is going to remain above the x-axis and therefore positive forever. And prior to 2, my slope, my derivative function is in the negatives, meaning my slope should be negative prior to 2 forever. And this is going to be a negative slope as we come from negative infinity. Okay? Any questions on that? So tonight, another multiple choice packet online where essentially they're gonna give you the function, or they'll give you the function, ask you to pick which graph represents the derivative, or they'll give you the derivative and ask you which graph represents the function. So the nice part about the multiple choice on this one is that there's no drawing it yourself. You'll have options to choose from and things to look at. Okay? Any questions?
Are we supposed to do it on a separate sheet of paper?
There's not really probably much work here, so you don't have to, unless you don't want to print it out. If you don't want to print it out, do it on a separate sheet of paper. But if you print it out, you might appreciate having that concrete. Yeah. All right, I'm done. If you want to, too, you can watch the YouTube videos.